This is from, actually, let me write it this way. So this is an example, and it's a sample problem 311. I don't know which page is that, but trust you'll be able, I trust you that you can find it. All right, so we have a foundation, right? We can look at it as a plate, right? Square, it's not exactly, so it is a square plate, 10 by 10. We have a square plate. 4 forces are applied to this plate. All these forces are parallel to each other. So it's very close to the special case number 3 when we were talking about special cases. Now, what we're asked to do is we are asked to find, let me write the problem statement. Square foundation, right? We have a square foundation, supports 4 forces, support 4. It's more like a civil engineering example, I would say, probably. We deal with that less. They say supports 4 columns, but it doesn't mean that you're not going to have the same situation in a mechanical system, pretty much. You can have a plate with 4 forces applied to it, depending on the system you're dealing with or trying to design. Determine the magnitude, let me get the wording right. Determine the magnitude and I think point of application of the single resultant force That's good enough. So remember, we said when we have a series of forces, set of forces, we can simplify that to a resultant force and a moment always. And we said also we can go one step further and simplify that to a system that only has just one resultant force by moving that force in that plate at some location, at some distance from the point that we found the resultant force and resultant moment about, to get rid of the resultant moment, right? It causes a counter moment or torque to cancel the moment that was created about that specific point at the beginning. By moving that force, we can get rid of that moment and have just the whole system with just one resultant force. And that's what this example is asking us to do. So just to make things a little easier, let's say I'll call this one F1, so we know what forces we're talking about. I'll call this, let's say, F2. I'm going to call this one F3 and this one F4. So it's easier to follow. All right, so when we are dealing with forces in 3-dimensional space, we said always we go for Cartesian coordinates, and what we do is that, well, both forces and let's find, so we're going to go step by step. We're going to find resultant force and resultant moment about point O. It's the origin of this coordinate system. Not necessarily you can go about finding it about any other point. You can solve this problem by finding moments, resultant moment, resultant force about any point you want. I choose point O because the origin of the coordinate system. We can choose any point. Once we get that, you are going to end up having a system with one resultant force and one resultant moment. And then from there, we can go one step further and get a system with just one resultant force. So considering that this is our coordinate system, this is X, this is Y, and this is Z. So let me use the color I usually use to answer. All right, so we start with, let's represent first forces. Right? What I want to do is that, keep in mind, I'm looking for FR, right, resultant force, and I'm looking for MR, resultant moment. In this case, I need to specify which point, so I'll take it about point O. So I'm looking for these two first. First step, right? Find the equivalent system that only has one resultant force and one resultant torque or moment. All right. So for the first one, resultant force, pretty much a summation of all the forces I have. I have 4 forces. I'll just put 1 to 4 would be F1 plus F2 plus F3 plus F4. And these are all vectors. Now, because all these forces are parallel, they are acting in the same direction. So it's pretty, I would say, straightforward to find this resultant force or summation. If I take the upward as positive, always choose one direction as positive. Take upward as positive here because I did that because y is upward, so it's positive. Just for the sake of completeness, let's write these vectors in Cartesian space, because that's what we always do. What is F1? Someone tell me. You know, I need a fast answer because it's easy. F1 in terms of a vector in x, y, z coordinate system, exactly 20. So minus 20j. Thank you. One quick note, I don't know if I mentioned that, but Kips, right, is pretty much, it stands for one, or just 1 Kips is 1 kilo pounds. 1,000 pounds. So when we're dealing with very large forces and we are using US customary system of units, we use kips, 1 kilo pound for. So these 20 kips mean 20,000 pounds. Just wanted to make sure that I mentioned that if I didn't mention it before. So F1, F2 is minus 8 J. Right? I'll just write them. Right? It's 8 kips downward. F3 is 12 kips, so minus 12 J. The units for all of them are kips. I have to be better and always put the units because I expect you to put the units. F4 is 40 and it's also downward, so it's negative J kips. So I have all the forces that written in coordinate in Cartesian coordinate system. So now I can find these. F1 plus F2 plus F3 plus F4 pretty much you can find this value by adding up these numbers. Right? All negative, downward, parallel. So it would be minus 20, minus 60, minus 80. Right? Would be minus 80 J kips. So I found the force, resultant force. Doesn't matter where because I'm finding it about 0.0, but because all they're parallel, it really doesn't matter. Would have been the same about any other point. Now, we have to find the resultant moment, mr, and I'm finding it about 0.0. Well, we don't really have any we don't really have any couple moment, like any couple free vector floating around. We only have forces. So all we need to do is we have to find the moments created by these forces about 0.0. So I'll write it like this. From 1 to 4, which would be M1 plus M2 plus M3 plus M4. I have 4 forces, so I'm assuming each force is going to create a moment about 0.0. Remember, I'm finding the equivalent system, so I'm pretty much moving all these forces to 0.0, and that moving, every time I move a force out of its line of action, it creates a moment. Right? And these are the moments that I'm trying to find. So to do that, I have to find the value or the vector, the distance between the point I'm moving the force and the point the force already, that force is already applied to the plate. So if you want to think about it, you can think about it this way. This would be the distances. Let me write it. This would be R1. This would be R. I call this force 2, so R2. I call this force 3, so this would be R3. So I'm going to add R vectors here. R is the distance between where force F1 is to the origin that I'm going to move the force there. Can someone tell me what that is? R1. And looking at XYZ coordinate, R1 would be the position vector from point O to point where F1 is applied to the plate. So R1 is in XZ plane, right? It's not going to have any Y component. What are its X and Z components? Four, 0, 10, 4i, exactly. Thank you, folks. Connor, Richard, and Sam. Appreciate that. So that would be 4i plus 10k. No, someone got it almost right. X direction 4, in Y direction, in Z direction 5 plus 5 gives you 10. All right, R2, position vector 2, right, the amount that I'm going to move the force F2 to take it from wherever it is to point O. That will be 10i, X is 10, this direction, and Y is 5, or better to say Z is 5, because they're all in XZ plane. Y for all of them are 0. So plus 5k. If you don't see it, let me know. R3, position vector, pointing from point O to point C in this case, where F3 is applied. So along the x-axis. So the only component it has is 10i. Just 10i. Thank you. Yes. R4, I didn't put it there, well, because F4 is exactly applied to where my final point is, which is point O, and it's the origin. So R4 is 0. There's really nothing there. There is no distance between where F4 is and the point O. Right. So now I'm ready to calculate M1, M2, M3, and M4. We do what we were doing before. Let me erase this part. Get rid of this. Now let's find these components one by one. M1 will be R1 cross F1. Do the cross product. Well, the first line is ijk, unit vectors. The second row would be R1, which is 4, 0, 10. Right. And the third line would be, or third row would be F1. Well, F1, the components are 0 except the one in J direction. So I'll get that one. If you do that math, you'll get, if I did it right, you'll get 200i minus 80k. And that would be kip fit. It's a moment, it's torque. Right? Force multiplied by distance. Do it for the second moment, M2. R2 cross F2. And the first line, well, these are just unit vectors, ijk, for the first row. Second row would be R2. I already found it on the right side in orange. It's 10, J is 0, and K is 5. And F2, it's 0 minus 8, 0. Oh, we can do a better job in terms of writing that minus 8. So it's more separated. So if you do that, all right, I skipped that part. Hopefully by now you're comfortable doing it either by hand or, as I suggested, I prefer you doing it by your calculator, using your calculator, or whichever method you think you're faster. that will give you 40i minus 80k. Again, keep, supposed to be keep. Yes, that was fast, Ocean. Thank you. That's good that you guys give me the answers, because as I told you before, I'm not very confident with my final numbers most of the time. So it's good to know that someone else also got the same number. So thank you, Ocean. M3, if I can type here, would be R3 times F3. That we might not even need to write the whole determinant. I can just write it as 10i cross minus 12j. It's going to save some time. 10 times 12 is going to be 120 minus 120. I cross j gives you k. Remember that unit circular draw. I cross j. You're going counterclockwise. I cross j gives you k, and it's positive. So that negative comes to the final answer. Keep fit. So we know M1, M2, and M3. What is M4? How do we calculate M4? Or what is exactly 0, right? Because R4 is 0, so there is no distance between the force and the point we're trying to find the moment about. So we're good to go. M4 is 0. Therefore, if you put all of this together, I'm going to draw a line here. So MR about O becomes M1 plus M2. Let me add this here. Right, this is pretty much 0, since R4 is 0. In case later on you look at it, don't be confused about what happened there. So we add them up. We have 200 I 40, so 240 in I direction. Nothing in j direction. K direction, we have 120 plus 80, 200 minus 280. Right? Minus 280 k. Keep fit. So far, we have FR and we have MR. Now we have a system. We found the first system equivalent that we have one resultant force and one moment. We got rid of all those forces applied at point O. Now, what we are asked to find is we want to find an equivalent system that only has one resultant force. And there is no moment, resultant moment. So, to do that, I have to move this force around somewhere in this XZ plane. I have to move FR, that I can get rid of the moment by the moment created by FR with respect to point O. So we kind of talked about this before. We said D, the distance, the vector that this has to move, this FR has to move to provide us with a system that only has one resultant force. So it is equal to MR as a vector about point O, let's say what we found, divided by FR. I can move things around to make my life a little easier. I can just write it this way. Instead of division, I can write it as a multiplication. Vector D cross vector FR. And I know the values. This one MR was 240, I think I, minus, let me check, minus 280. Minus 280 K is equal to, well, I don't know anything about D, vector D, so I'll just write it as some unknown vector with unknown components. Right? So I'll just write it as xi plus yj. Don't get confused. Confuse these xyz with xyz we use for the coordinate system. Right? It's just some unknown components for the vector. X amount in I direction, Y amount in J direction, and Z amount in K direction. Multiplied by, let me write it here, hopefully that's not confusing. And FR, we found FR to be, forgot that, minus 80J. All right, so I'll put it here, minus 80J. So, looking at both sides, right, I can do the multiplication on the right side and get the components. If you do this multiplication, you get xi times minus 80j. So you'll get minus 80k. Right, let me just do that, just to make sure that you don't get lost later on. Minus 280k, right, is equal to, you will get minus 80xk, which comes from the multiplication of I and j. J and j, cross product of j and j, they're two parallel unit vectors. Nothing comes out of it is 0. And you remember we talked about the cross product of unit vectors. And here k and j, well, it becomes negative. Keep in mind we have I, j, k. Would be nicer. When we multiply k with j, we're going the opposite direction. It becomes I, but negative. So that negative and minus behind 80 cancels out. We'll get plus 80z I. Now we have two equations, two unknowns. We can just find it. So a minus 80k and minus 280k minus 80kx equal to minus 280. You'll get x from there. And x becomes, I'm not sure what becomes. I'm just going to write it here and do the math. So this becomes a minus 280 is equal to minus 80x. And the second one, let me know if I'm making a mistake, 240 is equal to 80z. So let's see, x becomes, somebody has to do this math. Z, I guess I might have it, 3.5. Oh, it's 3, sorry, Z becomes 3, right? 3 times 80 becomes 240. So this becomes 3 feet. X becomes, I have a number 3.5, but somebody double check this, please. 3.5. Yes, thank you. So 3.5. So what I get out of this is that I get the components for D. So what this tells me, it says D, nicer D, D becomes 3I plus 3.5K. And this is what I was looking for. This tells me that if I move FR this amount on this plate, right, that this is what it's trying to say. If I have, let me see, relatively draw a plate there. If I draw the plate, let's put it the same plate you saw in the previous figure, right? And I have my vectors x, I can do better than that, parallel to this, and then draw this one there. Let's say these are x and z components, and this is point O. Isn't this supposed to be flipped? Yes. I have no idea why they put 3 for z and 3.5 for x, for k. You know what I mean. So it's going to be 3.5 I. This is going to be 3k. Thank you. So this means that if I move this force that was initially at point O and some moment there, if I move it d amount somewhere here, this is vector d, you can think about it this way. This is D. With these components 3.5 in X direction, 3 in Z direction. If I put that force here, now the system only has one force, and that would be just FR. So I went from that system with 3 forces parallel to this system equivalent that only has one force.